Alright, in this video we are talking about a reaction known as the Michael reaction. And what you'll see from this video is the fact that this reaction is very, very similar to the aldol reaction, the Claisen condensation, that sort of reaction, in that you have a species that has particularly acidic alpha hydrogens, which in this case is this beta keto ester. This would also work with a 1,3-diketone or dialdehyde or diester or something like that. This reacts with a base to form an enolate, then the enolate goes out and attacks another molecule. The thing that makes the Michael reaction different is what the enolate attacks. And it attacks an alpha-beta unsaturated carbonyl, and there's something special about this, because usually what we've seen before in enolate chemistry is that the negative charge from the enolate will go over and attack the carbonyl carbon, but in this case it's a little different. Right? Let me draw out this alpha-beta unsaturated carbonyl. And this carbonyl, it could be an ester, it could be an aldehyde, it could be a ketone, it could even be a nitrile. As long as you have this conjugated double, single, double system, or even double, single, triple if it was a nitrile, that's all you need. So, like we said before, usually when you have enolate attacking something, it usually attacks here. Alright, at this carbon. In this case, the nucleophile or the enolate attacks at this carbon. That doesn't seem to make any sense, but let's see if we can show some resonance arrows as to why this carbon in particular is electrophilic. Alright, well, let's try and push some arrows. Remember we said before, these electrons are conjugated, so I can push these arrows up onto here. And so I can actually generate a resonance structure for this alpha-beta unsaturated carbonyl. So let me draw this out again. There's my oxygen. And now I have a minus charge on the oxygen. I have a double bond here. And I've generated a plus charge on my N carbon. And that is the reason why this carbon is much more electrophilic than the other carbons in this molecule, and that's why when you form the enolate, it attacks here. Alright, so let's take a look at our mechanism. Let's assume we've already gone through the fact that the base has reacted with the acidic alpha hydrogens and formed the enolate. Alright, so let's just start off by drawing that out. Here is our enolate, and I'm going to draw it in red just like it is over on the page that we were just on. So here is our enolate. This is one resonance structure of our enolate. Alright? Because that's what we started with. In fact, we had an ester there, so let's put that here. And then I'm going to draw out, oops, went the wrong way. I'm going to draw out our alpha-beta unsaturated carbonyl as well. And let's put that right here. Now remember what we said. We said that in the Michael reaction, when we have an alpha-beta unsaturated carbonyl, and this is the only time this happens, is that when the enolate sends its electrons down here, and these electrons go out when they would normally go up to here, in this case they don't do that. They go to this end carbon. Remember we showed the resonance structure for why this is actually a very electropositive carbon. These electrons then kick down here and ultimately kick the electrons up onto the oxygen. Alright, so let's see if we can draw out what the product of that looks like. And I'm going to draw it out with what was the enolate up on top. So let's draw that out. So here is our enolate. Alright, here we go. And that's the product of our enolate reacting. I'm going to draw in black the new bond that we've formed, because we've formed a bond between here and here. So I'm going to draw that bond. Oh my god, that bond has problems. Let me erase that. That bond looks like it's seen a little too much alcohol. Let me try and draw that in again. Alright, there is our lovely straight bond. There we go, that's textbook. Alright, now, let's just count our carbons here, okay? 1, 2, 3, 4. So that means this carbon here is going to be carbon 1. Alright, this carbon is going to be 2. This one's going to be 3, and this one's going to be 4. I'm going to draw the minus charge down here simply because I don't want my oxygens to get all mixed up with each other. Can you guys see now where my double bond is? It's between carbons 2 and 3. If we said this was 1, this is 2. It's supposed to be a 2. This is 3, and this is 4. We have a double bond between 2 and 3, so right there. Alright. And this is where things get a little bit different from this sort of reaction. We have ethanol lying around that we generated in this very first step. The ethoxide grabbed a hydrogen and formed ethanol, so I'm going to draw some ethanol out. Let's just say here is our ethanol right here. Okay, there's our ethanol. These electrons from this oxygen are going to do what they've always done. They're going to come down here, and when they come down here they send these electrons out, exactly the same as we saw here, except now we don't have any nucleophiles to attack, so any electrophiles to attack, so we're going to go and grab a hydrogen instead. So grab that hydrogen, and if we do that we have to break this bond. Alright, now let's try and draw out what we get here. We're actually going to get something virtually identical to this, so let me draw out the top red part first. Alright, there is our OR. Here are 2 carbonyl groups, and I'm going to do what I did before, put the bond that we formed here in black, and then add all the rest of the stuff in. Alright, notice the double bond that we formed is the carbonyl group. Alright, so in doing so we form ethoxide ion again. Now, any ideas for what you guys think might happen next? Because this is something that we have seen before. This essentially is our final product, but we've formed ethoxide base. And do we have some very acidic alpha hydrogens around anywhere? Well, before we answer that question, even though we know it's all going to be yes, take a look at the reaction steps here. This is similar to the Claisen condensation, in that there are 2 steps here, and we've only ever dealt with 1. We haven't dealt with the H3O plus yet. And there's a very simple reason why the H3O plus is in the second step as it is in the Claisen condensation. That is the fact that this extremely acidic alpha hydrogen is present. Alright. And in exactly the same steps as you saw for the Claisen condensation, the O- grabs the hydrogen, forms the enolate, which then has to react with acid to reform the product. So what you ultimately get is this reformed but with no ethoxide around. So that hopefully looks very similar to what we had on the first page, and what do you know, it does. It looks a little bit different, but if we just count our carbons here, the carbons that we've joined together here, 1, 2, 3, and 4. If I do so here, I should be able to count the same number. 1, 2, 3, and 4. Essentially where there's 2 CH2s, a carbonyl and a CH3. Let's just check that that's the same. 2 CH2s, a carbonyl and a CH3. So we have done that right. So that in essence is the Michael reaction. It's very similar to the Claisen condensation, except that you're adding to the alpha, beta unsaturated carbonyl, which means you add on the N carbon rather than the carbonyl carbon. All right, and that is the Michael reaction.